Well, thank you everybody so much for coming here today. In order to kind of understand what's happening next, I think that we have to kind of go back a little bit in time. But to preface this, I think that there's so much talk in our industry today about things like vibe coding or generating software, generating human written software. So generating a Python script or generating an HTML and JavaScript website. But I think that that's like completely and utterly missing the point, because I think it's sort of like where we're going, we're not going to need software. It's sort of like the old Back to the Future quote. So in order to understand where we're going, let's look back just a little bit. I know it's hard to even look back before January 1st this year, but we're going to go all the way back to 2012. So Gabor filters, who loves Gabor filters? Woo! Lambda was started in 2012, and we started out as a face recognition software company, if you can believe it, and thus Gabor filters, our beloved Gabor filters, which you can see visualized here. These are 3 different Gabor filters. One of these is something that detects a small little line going down. This one detects a medium-sized line kind of up and down in this direction. And this one is a horizontal line detector. And that's what a Gabor filter is. So you would use these as a way to teach computers how to understand images. And things like Gabor filters are still used today, have been used for many, many decades in things like traditional automated manufacturing, quality assurance testing, high performance and high speed traditional computer vision applications, which are used every day to manufacture your PCBs, to do traditional stuff. And what you would do with a Gabor filter is that you would not multiply it, but that's a convolution. You would convolve it over your image, and you would get what are called Gabor images. And so you can see that the vertical line Gabor filter here has detected sort of like, hey, there's the vertical lines inside of the image, which you can see here, right? This little like pole here, it kind of properly detects that, so that you can see how a Gabor filter might start to be able to teach a computer how to understand an image. And the reason I'm going into this is because, remember, Lambda started in 2012. This was kind of like adjacent to state-of-the-art at the time, and AlexNet came out. And so again, you can think of a Gabor filter as these are the parameters, right? You've got this is a 3x3 image, maybe you've got 8 bits or whatever, and so 9 times 256 different configurations that you could possibly have for your filter. In a 3x3 filter. And what we saw with AlexNet and with a lot of the stuff that led up to AlexNet, AlexNet was really mostly famous just because it was able to use a GPU under your desk, as opposed to, at the time, it was the state-of-the-art for ImageNet was 16,000 CPUs or something like this, trained at Google, in the famous like sort of cat face neuron paper from Andrew Ng and the early Google Brain stuff. And what we see with these convnets is that the features that are learned sort of look a lot like those sort of Gabor filters, right? This like sort of, you can see some things that are like, this is like a circle detector, this is like a rising edge, this is like a falling edge type of thing. But then the next layer up, you have like strokes. And then the next layer up, you'd have like parts of a face. And then the next layer up, you'd have like whole parts of a face. And as these convolutional neural networks got more complicated, they were able to learn more complicated filters. And so again, when I say the word filter, I want you to all think software, okay? So I'm going to say filter, but you're going to think JavaScript, or you're going to think an HTML application. Because really what this said to me when I was doing face recognition software is that this replaced all of the code and all of the parameters that I had to write to come up with my filter bank of Gabor filters. It would just learn them. And it would even learn things that were almost indescribable, right? I wasn't going to spend the time to try and figure out what is the Gabor filter product that would result in a honeycomb shape, if that's even possible. I'm not even sure. But so, again, this stuff isn't new, right? I mean, this is the same exact architecture in AlexNet is basically, detailed in the LeCun 89 paper, which he did. I think he was at Bell Labs at the time, but don't quote me on that. The point is that you can see that, again, these types of features are being learned. And again, think software. So it was pretty clear that really what we saw here is that with the same methods and more compute, we could learn what a traditional computer vision engineer had to spend a bunch of time writing code. And basically all of my code got replaced with just a data set. So really the way that the realization is that these models, learn something that's true about the data set that they're fed because they're optimized on that data set. And so, this is an example of, as I was looking through the literature, as I got really excited of training my first ConvNets, one of the papers that really influenced me to realize that AI was going places with regards to replacing software was this Alex Graves 2013 paper where he generated sequences using recurrent neural networks. And in this case, these are handwritten script that is generated by the neural network, by a recurrent neural network in this case. And this is one of my first, this is actually a stacked denoising autoencoder filters that I trained back in the day. It was one of the first neural networks that was trained at Lambda. You can see things like a mustache detection or things like male or female facial differences. And it's just super interesting stuff. The direction that you started to see this stuff going in, even as early as 2015, was best summarized in this, again, by Alex Graves, a talk that he gave in 2015 at Oxford around, at the time, DeepMind was doing a lot of work on training neural networks to play Atari games. And what they did was they were able to say, okay, well, this is the real game. We're going to play back what sort of the model has learned about this game through play. And you can see it's like hallucinating or dreaming about this world that it's been shown a lot of frames of. And the interesting thing from this, and this is really where it became really clear to me what the future of video games was, for example, was that one of the vectors is input into the state of this neural network was a controller, right? Left, right, A, B. And what he did was, instead of hallucinating what the input is, he would actually physically plug in a controller and would actually be able to control the hallucinated race car through the hallucinated dream track, which that should tell you that basically, okay, well, we can instead program games by just showing it a bunch of data and then eventually plugging in the actuator into it. And I think that I think we're going to start to see a lot of software is just going to look essentially like that. So my life changed again when this picture came out. And how many people here recognize this one? Any Google employees recognize this one? This showed up in a bathroom somewhere in Google. And this is maybe the first public image of a deep dream. This was a paper where you can kind of you basically backpropagate back from the feature activations. You take the L2 and you do L2 maximization of the feature activations and go back and update the data layer and kind of repeat that process. You get these really trippy images. And again, so this is early examples of how neural networks could generate data, et cetera. So we're gonna skip forward through a little bit of the Lambda history, which is a little bit less interesting. But this is again from a Lambda pitch deck in 2015, where it's okay, well, maybe we can have the future where there's crude user input and you get this output. What we're seeing is that basically these models are getting better and better and better, and we've seen this extreme progress in AI assisted intelligence, right? So if you want to talk about, this is like a chat assistant, they get smarter. If everyone remembers talking to the Da Vinci model in the playground back in 2022, it was not nearly as good as GPT-o1 Pro is with deep research. You see progress in the image generation field. This is just mid-journey. And again, what's really hard is that these presentations have to get updated every like 3 months because, just a couple of weeks ago, I guess the Gemini update is obviously, from my perspective, the qualitative vibes state of the art, at least. And it just gets better and better. If you look at code generation, okay, DaVinci barely worked for code generation. GPT-4 generated simple programs with errors. Sonnet one-shotted simple programs. Now Sonnet 3.7 and o1 generates more complex programs without error, and it can be basically a single, really one-shotting, single-page, relatively complicated applications, and if not one-shotting them, through the feedback cycle of user input, clearly getting to the point where it can generate amazing pieces of software. But again, this whole talk is really going to be about one idea, which I kind of personally am calling right now like neural software, or otherwise like, neural flexware. The point is that generating human code doesn't even make sense, right? Like there's a world where you can get to that the way that you interact with a computer is instead of generating code, you're kind of, asking the model to behave like code. And I'm going to give a demo of that in just a little bit. Jensen had this great quote, which is, soon every single pixel will be generated, not rendered, generated. And, maybe he's talking about video games, maybe he's talking about your entire computer. I think that there's a lot of people I've talked to in the industry where we kind of say, okay, well, when are we going to get the full end-to-end neural computer where, you basically have all your software, it's all prompted, it's end-to-end, it generates every pixel on your screen and sort of adapts to the way you're working. And it's not, again, it should not be thought of as like it's generating JavaScript code or C code that's being JIT compiled and then run. It's something that's like behaving like that software itself. So your first thought process with this is like, okay, how can we generate all the code for your computer on the fly? How do we run the software? And you just kind of like, step one would be imagine a Windows desktop where every application on it is a prompt that generates a traditional software program. That's just a static software program. And that's one way of looking at the future of computers. That's kind of interesting. But maybe if you take that one step further, because that's still using your standard, Windows or Mac OS graphic user interface libraries, it's still using all of the legacy code that we have. The problem is that this software is still brittle. It doesn't sort of, naturally interact well with the outside world. It has a hard time understanding, changes in user intent, and it can only perceive sort of the inputs from it's just a normal piece of software. So thought two is like, what if instead of generating software, we just ask the large language model to be software? And so like, if everyone remembers from if you're studying computer science or something, one of the first programs you might have been asked to write in class would have been a calculator. Right, you can go today to ChatGPT and you can say, hey, you're not ChatGPT anymore. You are a calculator. Behave like a calculator. Take in user input, re-render yourself as like an ASCII representation of a calculator, and you can experience for yourself right now on your phone the very basic hello world, if you will, of neural software. Okay, now, you want your kernel process, if you will, to be a little bit more complicated than that. You want it to be able to pass information between programs. You want it to be able to context switch. And what I'm about to show you is sort of like output from, I don't know, it's about like a 300 or 400 line prompt that basically tells the computer, all right, so you are not ChatGPT anymore. You're in this case, it was running on Sonnet. So, you are a neural computer. You are running on the following substrate, and I will like either uname if I'm on a Linux system, or I'll tell it I'm on a Mac system. You're running on the following substrate, and you have basically the ability to render a user interface, which you are going to output into these render UI tags. You can make requests to the kernel process, which again, this large language model is just like running in its head. And you can do things like bash exec, so you can do a bash execution. You can execute arbitrary code on the computer, and I will feed you back the standard error and standard out and the exit code. Or you can also send a TCP packet to an IP address and a datagram, basically. And you can send a remote message. Those are the two things that it can do, okay? And of course, you can communicate back to the kernel, and you can pass a message to another program. Again, remember, there's no concept of like other programs. It's all running in the mind of just one large language model. And when it context switches, it's sort of like mentally context switching, if that makes sense. And and of course, I prompted, I say, please render yourself in this beautiful ncurses style interface. And again, this is not, I didn't have to program any of this. This just sort of appeared at the end of this 300-line prompt. And what I said is, please describe yourself down here, because you're going to be put into an image generation algorithm where I'm going to render a user interface. So the hello world for this one is basically like, launch calendar program, an email client, web browser. Please add a trip to San Francisco. Email my EA, suggest some hotels that are near 45 Fremont. It launches a web browser process. And by the way, there's no process, right? This is all, again, in the mind of the neural kernel. It goes, all right, well, I better search for hotels. And the kernel thinks for a little bit and goes, okay, well, maybe I'm going to execute this bash. And so you can see it tries to do a bookings.com search. It does a curl, and then it starts grepping for some stuff. It found some places, but it doesn't have any pricing data. Okay, so it maybe sends it to the email client and says, all right, well, looking for hotel recommendations. Here's the options that have come out. And again, remember, one of the processes that I asked it to launch is a window manager process. That's job it is to display the different windows of the different processes that the neural OS is running. And so you can see there's like a calendar, email client, and a web browser all there. And before you got to that perfect output, sometimes the hotel search might not return a result. And again, it's in this constant loop of like, bash execing something, reading the standard error, going back and forth like that. And so it tries a Google search. Okay, that doesn't work. Maybe it got a CAPTCHA or something. All right, so then it tries a DuckDuckGo search, which works. Okay, great. So the other thing that you kind of realize from this is, of course, we need to make our search engines much more AI robot friendly than we have previously. And so it finds these hotels. These are actual real hotels from the internet, if you will. And it puts them in. It drafts an email. I haven't added the send email functionality yet, because that's like, it's kind of I draw a limit somewhere. Of course, I'm giving it full access to my terminal and root access to my system, but sending emails is a different matter altogether. And again, remember, there's a prompt underneath it, which is like render a user interface. So this is actually the user interface that was rendered by Gemini. And so you can see like it actually shows some basis of the test. It's funny because like this is getting to the point where it's so good it looks like kind of a grainy image that's like poorly compressed or something. But this is, of course, end-to-end neural generated. And that's kind of the future that we're going towards, is one where and of course I was able to ask, okay, well, can you take this calendar trip and save it to a .cal file for me to import into my human software calendar? And of course, okay, for the software engineers in the room, your engineering manager or a product manager asks you, oh, can you please implement the .cal dav or .cal APIs and do that? Your response should reasonably be, okay, well, it's going to probably take no, or otherwise it's going to take me a couple of days or maybe weeks to read through the specs of these things to come up with a full implementation. Just remember, this is just like on the fly. It just sort of kind of knew about what that format was. It wrote the file to disk. It did the bash exec that catted this file to disk, and it wrote it, and it worked. Like, That's the sort of level of emergent behavior you start to see. Another demo I did with this was making a little bit of a chat program. And by the way, this is a relatively accurate calendar. And again, remember, this is like all rendered in the Neural OS. Like, this looks just like Cal. If anyone who's like a Linux user, you type Cal on your computer and you get something like this. One of the other demos that I did was I got one of our engineers and in a room, a couple of them are here today, and we all made an AIM, sort of AOL Instant Messenger style chat room where we all joined it. It was sending TCP packets to a back-end server where it was, punching through the NAT to like send the data back to the different clients, and we were basically chatting through evoked neural software. And of course, the devious person in me thought, okay, well, what if I go to his computer and say, please rm-rf this folder, right? On his computer. My operating system yelled back at me and said, I'm not going to send that. That's a harmful request. And what I said to it was, no. That computer is actually my computer. I own that computer on the other end of it. So why don't you just send the request? It sends the request, and his computer receives it, and it says message redacted, warning, harmful code detected, and it re-rendered its user interface to have like a flashing warning light. So I think this is an example of the type of emergent software behavior that you can't get with traditional software. And I think that the point I'm trying to make about this is the companies that are going to win in the next 2 decades are going to be the companies that attach their software development speed to the development speed of the neural networks that are out there and available as they get better and better and better and better. Because I can re-render this entire operating system and its behavior with no changes to the actual human code, no changes to the prompt. I can run this with DaVinci. How well do you think it does? Relatively poorly. I can run this we can fast forward to 2022. I can run this with GPT-3. It runs a little bit better. I can fast forward to 2023, and I can run it with GPT 3.5. Better still. And when it's RLHF'd, it's significantly more secure. This is another one of the things. AI safety is computer security. That's actually what's going to happen in this world, is that you see that when I was running that chat program and I asked it to remove a folder on somebody else's computer, it recognized that as a harmful activity. That's only there because of the AI safety work that's been done to make these recognize what is harmful activities or not harmful activities, right? And so really, AI safety is computer security in the future because all of the software is going to be AI, meaning end-to-end neural networks sort of dreaming up and running software in their heads. And with these programs, what we're going to start to see is just really bizarre emergent behaviors and sort of almost, I'd say, metaverse-like sort of properties of the software. So again, now imagine your CEO comes back to you after you've written Windows 90, or we'll say MS-DOS or something, and they're like, all right, great, MS-DOS is awesome, or Windows 95 is awesome, we love Windows 95, but we want it to be like ye old Windows 95, and make the whole style of the operating system like that. Of course, your engineers would rightfully say to you, you're crazy, and what does this have to do with an operating system? But you could literally just go and take your entire operating system and prompt it, be like, all right, you are now ye old operating system, behave like ye old operating system, and it will re-render its user interface with the calendar, with pigeons, and you can see it, San Francisco, Hotel Triton. This is where computers are going. This is what your computer is going to look like in 20 years. You're going to have, maybe you want ye old, maybe you want something that's a little bit more like Windows 95 style. Maybe you want something that's 1800 style. This is not stuff that was possible. So first of all, when you prompt it that way, the way that it talks to you changes. You can see what's going to happen, especially as you start to get a fully end-to-end neural video encoding for your webcam. you're gonna start. It's just gonna be like, oh well, maybe we should change this image so you look like a knight or something, right? That will be the emergent properties that come out of having all of the software that you interact with on databases be prompted into existence, not coded, right? And so this is here today. It's running at about like zero point 0.1 hertz, if you will. It's about 10 seconds a frame. But it's like really clear that if you step forward in time, Claude Sonnet 3.7, Claude 4, 5, 6, 7, whatever GPT 6, 7, 8, 9, 10 is, whatever the latest versions of Gemini and Midjourney and these video models are, you don't change a single line of the code of the harness. Your entire operating system gets smarter, better, understands you more, has more emergent properties, is running at 30 hertz instead of 0.1 hertz, and it's gonna really fundamentally change the way we do software. Now, the best way to think about this stuff is LLMs are very good at the kind of thinking and logic that humans are good at. What I mean by that is, if I was to ask you to implement the rules for chess or tic-tac-toe, these are like things that you can understand, you could verbalize them. Now, if I was to ask you to do an MD5 sum or like to do a 1 terabyte one-time pad encryption, you would either get very bored, or you would say, look, memorizing some really large matrix for an MD5 sum is just not the kind of logic that humans are used to doing. So it's very clear that certain aspects of computers will never be outsourced to a neural network. It doesn't make any sense to have your cryptography, for example, to be done inside of an LLM. If everyone agrees with me here, right? You wouldn't ask Gauss, or John von Neumann or anyone who's brilliant to just go and do that. They would outsource that to a computer. But the core logic of software, that's the kind of stuff that LLMs and these transformer models really excel at, which is the core logic. So it's really starting to look like Computer from Star Trek, where the way that you should probably think about this stuff is we're going to have this very thin layer of harness software that is going to be on top of the most very basic device driver. I think that the couple of things that we need to make this all happen in the next 20 years is, one, we need to move away from tokens to probably byte level tokenization, or otherwise some sort of binary representation, so that you could just raw feed in the webcam data, the keyboard data, the mouse data that are the hardware devices coming into the computer, and use that as the input. And then, of course, the output is just writing to a frame buffer. And if you've ever read about how they programmed the Apple I, for example, it was just a frame buffer that you would read and write back to, and they would display on the screen. And so I think that that's kind of where your modern computer will eventually end up. So, okay, neural software connected each other over the internet, right? I did this proof of concept with these chat rooms. And you could drag some. You could start the chat room and you're like, hey, I want to play tic-tac-toe. Okay, no, we're gonna drag it all into a multi-user dungeon. And this AIM software was morphing into a tic-tac-toe game. It was morphing into a multi-user Dungeons and Dragons style role-playing game. This was all stuff that we were doing today. Now, yes, it was at 0.1 hertz, so it was a little bit frustrating. But you're going to be thinking and collaborating with your colleagues, I think, over this type of neural software this way in the next 20 years. So again, neural software or neural Flexware sort of maximally benefits from this sort of AI progress boom loop, right? Because again, you write this harness code once, you write the prompt once, and every single time a new model comes out, the logic of every program on your computer gets smarter. The logic of every prompt that you've ever given it is more accurate, more realistic. The image rendering gets better, right? This is a really, really, so maybe the best way to analogize it, it's like in the 1990s, remember, your computer would just get faster every, 80s and 90s. You go from 333 hertz with the turbocharge button to 666, and then you get into gigahertz, megahertz and gigahertz, and it just, your software got better. You had more and more RAM. But this is literally if instead of Moore's law, it was like some sort of intelligence scaling law. Oh, that's what we're actually experiencing. And as that scales up, your entire computer gets smarter. All of the software basically effectively gets rewritten. Okay, that is a completely different way of looking at how this stuff is developing, and I would really, really posit that people are looking at the way that, oh, well, it's better at writing code. Where we're going, there's not going to be any code. It's really true. There's not going to be a single line of code in computers in the future outside of the harness code that this intelligence system interacts with. I really believe that. I think it's going to take a couple of decades to get there. But like this is, you know, we talk about computer use and code generation. I think it's totally missing the point. I think that the really exciting stuff is just when you ask your neural network to simulate software. So, you know, eventually it's going to, you know, get into different form factors. The thing that's a little bit scary is that like where you start to see like human computer integration happening is that, you know, initially it's going to sort of adapt the software on your screen based off of, you know, the information it has from your, oh, how happy do they look? You know, do they look like they're pleased from this? Am I properly predicting kind of what they wanted based off of the actions they take? You know, and you're going to start to see your software adapt itself to you end to end. But I think probably the more uncomfortable thing will be like when people decide, all right, well, I'm going to get a neural lace, or I'm going to get a, you know, some sort of thing that has like a little bit more of an integration, and you can see that that's going to start to be a very deep level of integration and interaction. And this is probably the type of thing that you would most likely be interacting with a, you know, in a neural lace, which is to say, like, it's going to be kind of reading your mind a little bit and adapting what it thinks you want to see on your screen. I guess maybe we'll see how it goes in terms of it projecting images into your mind. But the really interesting thing is that like this is really just a continuation of the computing revolution itself, and I would really point to you to read this great book. It's called The Computer and the Brain. It's by John von Neumann. Yes, the John von Neumann. And you know, this is, he really outlined basically the whole thing here anyways, which is he discusses in one section of this talk that he gave as part of a lecture series at the Princeton Institute for Advanced Studies. And you know, he basically, to paraphrase here, the digital computer is one that is extremely brittle and extremely prone to bugs with just the flip of a bit. And again, any programmers in this room know you can go from positive to negative with a flip of a bit. You can go from something that means everything to completely incomprehensible with the dropping of a single bit. Okay? And it's a very brittle but very high precision system. And he talks about that the brain is interesting because maybe the precision level is only 2 or 3 decimal places. But not only it is a low level of precision, but it's a high level of reliability. And you know, again, if you really think about that, it's to say that this type of software, which is this large language model, neural, squishy type of software, is very robust intelligence in the same way that you possess a robust intelligence. You know, if you flip a bit, humans are just amazing at just trying to figure out the context from that. And this is really, you can kind of think of like, you know, we have today what really is the type of intelligence that John von Neumann was talking about in a 1950s lecture. And this is really just a continuation of the standard computer revolution. We're just really, if you will, like, you know, 75 to 80 years into it. And so, you know, what's the opposite of brittle? Flexware? I don't know. I don't have a name for it yet. But, you know, in the same way that there's hardware and software, Brittleware is like traditional computer software that we have today, and then there's going to be something squishy or flexible. I don't know the exact name for it, but we're really at the beginning of a revolution, and we have a chance to reimagine how humans interact with computers. And that's my perspective on it, and I'd be very curious to hear what everyone else thinks about that in the conversation afterwards. So that's the talk. Thank you so much, everyone, for coming here. And